Okay, students, the topic for this lecture is going to be matrix norms. Okay, so you remember in the very first segment, the beginning, the initial lectures, we discussed the notion of norms for vectors, right? So the main idea of norm is to quantify how large something is, right? For example, when you're dealing with vectors and you want in some sense to indicate how large the vector is, that's when we use norms. Okay, just so that norms conform to our intuition of what norms should mean, we have certain axioms that norms must satisfy. Okay, so just a review. So you remember that when you were dealing with vectors, we had these norms, right? So we said that whenever you scale a vector, the norm must just get scaled by the corresponding scalar, okay, alpha. So this is like homogeneity, right? This is one of the main properties. Basically, norm for us ties with the notion of distance, right, or how large the vector is, how far the vector is from the origin, right? So the homogeneity was one of the properties, and similarly we had definiteness, meaning that if a vector is 0, if the norm of a vector is 0, then we must for sure be able to say that the vector is actually 0, right? In other words, if your vector is non-zero, if the vector is non-zero, the norm must not be 0. Okay, so that's positive definiteness. And the third property, of course, norms are always non-negative, right? So norms represent distance, they're always non-negative. Okay, and the third property was triangle inequality, right? We said that when you have the norm of x plus y, that's less than or equal to norm of x plus norm of y. These three axioms ensure that whatever definition of norm we come up with, it fits our intuition of what distance is, right? And we looked at variety of norms. We looked at the standard Euclidean distance, which is like the sum of square roots. Square root of sum of squares. So this is like summation of xi square, and the Euclidean norm was the most convenient for us to analyze, precisely because you could write the Euclidean norm as a square root of an inner product. Okay, and inner products bring in this rich structure, linear algebraic structure that you can exploit. Okay, we also had other notions of norms though, right? We had all the p norms. We had the Manhattan distance, the one norm, which is the sum of absolute values. We had the infinity norm, which is the largest absolute value contained in the vector. Okay, fine. Now we try to do the same thing for matrices, right? So given a matrix A, how do I quantify or how do I characterize how large the matrix is? Okay, why do you even need to do this? We'll see a few applications in the remaining portion of this course. We'll see one application in this lecture itself towards the end, right? Why you may need the concept of a norm for matrices. We will see some other applications later on. Okay, so how do you quantify how large a matrix is? Well, one idea, and we have seen this before, right? One idea is to simply think of a matrix as a collection of numbers, just like a vector, right? Think of a matrix as essentially a large vector, but just written in a weird way, right? In a vector, you typically write, it's a column vector, you just write from top to down, but a matrix, you're just wrapping it around, for whatever reason. Just if you use that perspective of what a matrix is, then it's very clear. One norm you can easily define to be simply, just like you have defined the Euclidean norm, you can simply define the sum of all the squares, right, and the square root. So ij equal to 1. So here you are effectively treating your matrix as if it's a vector, and you're computing the 2 norm of that vector, right? And then what does that mean? That means that simply you take the square of all the matrix entries, add them up, and then take a square root. Okay, so that gives you the one of the ways to obtain a norm of a matrix, how large the norm is, right? Because this is already like a 2 norm, we know that it will satisfy all these properties. I don't have to reprove any of this stuff, right? Because this is effectively a 2 norm when you simply stack all the columns of the matrix one below the other. Okay, so intuitively it's not really much different from that, right? So these properties it will satisfy very readily. Okay, but the issue with this norm is that we have to remember that matrices are much more than just a rectangular arrangement of numbers, right? This is the idea that we came up with, we thought of even in the very first segment, and we used that to come up with some interesting observations, right? So same case here, it is probably a lot more instructive to think of a matrix not just as an arrangement of numbers, but as something that is a system, right? Something that's an operator, right? Something that takes an input and spits out an output, for example. Okay, so you think of a matrix as something that has an input and an output. Essentially, the main idea is that you can multiply two matrices, right? And that multiplication has a very rich structure. Okay, it's not just an arbitrarily defined multiplication. Okay, so we'll try to see how this norm behaves with respect to that multiplication or that operation. Okay, this norm is called the Frobenius norm, and again we have defined this in the earlier segment. We had to rush then because, as I said, the first segment was supposed to be like an overview. So there are a lot of concepts that I had to rush through. Okay, this is the Frobenius norm. Okay, the Frobenius norm of a matrix is just the sum of the square root of sum of squares of the entries of the matrix. Okay, now just like your two norm for vectors can be very easily analyzed because it can be written like this, an inner product. Same way, Frobenius norm also is much relatively easier to analyze, one could say, compared to the other norms. Okay, in particular, you could write the Frobenius norm as trace of A transpose A, square root of trace of A transpose A. Okay, that's the Frobenius norm. This also we discussed in the first segment, right? You can very easily see that when you compute the trace of A transpose A, remember what is A transpose A? It's like the gram matrix of A. It computes the inner products of the columns of A with themselves. So the diagonal entries of A transpose A are simply the norm square of the columns of A. So when you take the trace, you sum all the diagonal entries. So you go to sum the norm square of all the diagonal entry of all the columns of A, which is essentially the same as this summation. Okay, we went over this in the first segment. If you are in doubt, you can just take example 2 cross 2 matrices and see that this all works out. Okay. Because of this reason, because of the fact that you actually get A transpose A, notice how this mimics very closely what happens with matrices. You have X transpose X here, the inner product of matrices. You have A transpose A and the trace. And for this reason, I mentioned that this is also like an inner product on matrices, right? Trace of A transpose B can be thought of as inner product between matrices, or dot product of matrices A and B. Okay. Once again, that intuition follows very easily if you realize that trace A transpose B is actually nothing but you just take every entry of A, multiply with the corresponding entry in B, and just sum them up. That's what will give you trace of A transpose. Okay, so it's effectively like the inner product of matrices A and B when they are just treated as vectors. Okay, or a stacked. When you just treat them as a rectangular arrangement. Okay, so this is what the Frobenius norm is, and we discussed the Frobenius norm also in the beginning of this course. So here, what I'll try to do is I'll try to look at some very interesting properties of the Frobenius norm. Right? In particular, how does Frobenius norm behave with respect to matrix multiplication? Right. So this is one of the first operations that uses a lot more than just the fact that matrices are rectangular arrangements, correct? So how does the Frobenius norm of a product of matrices relate to the individual Frobenius norms? Okay, well, to make things a bit simpler for myself, I'm just going to put A transpose B over here. Right? I'm going to write the trace of the Frobenius norm. By the way, the Frobenius norm of any matrix is the same as the Frobenius norm of the transpose of the matrix. That goes without saying, right? In fact, if you randomly permute the rows and columns also, the Frobenius norm will not change. If you reorder the elements also, however you want, it will not change, of course. Right? Okay, so the Frobenius norm of A transpose B, I'm going to claim that this is less than or equal to the Frobenius norm of A multiplied with the Frobenius norm of B. Okay. You can easily see this, that the Frobenius norm of A transpose B is less than or equal to Frobenius norm of A into Frobenius. So why does this follow, right? So let's just look at every entry of A transpose B, right? So for example, once you multiply A transpose and B, you get a matrix over here. Let's look at, let's say, the first entry, the top left entry of A transpose B. What is this entry? This is actually a dot product of the first column of A with the first column of B. This is not, right? This is like a dot product of the first column of A with the first column of B. Now, when you take the square of it, right, So this is like, so let me call A1 as the first column of A and B1 as the first column of B. This entry is precisely that, A1 transpose B1, right? When you take the square of it, I'm going to simply apply the Cauchy-Schwarz inequality and claim that this is less than or equal to the 2 norm of A square, the 2 norm of B square. Okay? Meaning that this entry over here, when you take its square, is going to be less than or equal to the product of the 2 norm of the first column of A and the 2 norm of the first column of B. Okay. 2 norm of the first column of B, right? And similarly, you can write this for all the entries, right? So the square of each of these entries is going to be less than or equal to some product like this. Okay. When you add them all up, what you get is the Frobenius norm of A transpose B whole square. Correct? By definition, Frobenius norm of A transpose B whole square, that's less than or equal to, you're going to get a sum of a bunch of such terms. Right? So here you are going to get the 2 norm of the first column of A times first column of B. Here you are going to get 2 norm of first column of A square multiplied with second column of B square. Here first column of A square, third column of B square, and so on, so forth, right? When you add all these terms, what do you get, right? But just by taking things common, you can actually see that you will get the Frobenius norm of A square times Frobenius norm of B square. Okay, it's a very good exercise for you to carry out. I'll leave this to you. I think it's not very difficult. Just take a few examples, right? So just take A to be like 2 cross 2, B to be 2 cross 2. This will become a 2 cross 2 matrix, and just work this out. Okay, you will see that. The key idea is to apply Cauchy-Schwarz inequality for every entry of this matrix. Okay, so this property here is something called submultiplicativity. Okay. Submultiplicativity essentially is saying that when you multiply two matrices, of course I can get rid of the transpose, right? Because the transpose doesn't really affect affect anything. For example, here I could write A transpose, Frobenius norm of A transpose times B, and I can just call A transpose as some other matrix, right? So the Frobenius norm of AB is less than or equal to Frobenius norm of A times Frobenius norm of B. This is called submultiplicativity. That's when you multiply two matrices, the norm of the product must be less than or equal to the norm of the individual matrices. Right? It turns out that for many situations, many applications and many results, submultiplicativity is a very desired property. Okay? It's a very desired property. I think going into details too much, maybe a bit not very productive at this stage, because it will go slightly out of the scope of what we're trying to do. But submultiplicative essentially is a desired property. Okay, so in addition to the standard properties that norm have, these properties, right? So the main point I'm trying to say is that these properties don't enforce any operator structure on the matrix or any system structure on the matrix, right? These properties are true even for vectors, but when it comes to matrices, you also want a norm to satisfy this additional property, right? It is submultiplicativity, and the Frobenius norm ends up satisfying it, which is very good. Okay. So main thing to remember for Frobenius norms is this equation, right? Almost anything you want to derive can be done from this, right? So the Frobenius norm of a matrix is square root of the trace of A transpose A. Okay, fantastic. Okay, so let's look at some very interesting properties. Well, I'll call this as the first property of a Frobenius norm, submultiplicativity. Right? Let me look at another very interesting property, and this also we had looked at before, right? So suppose if you have a unitary matrix and you multiply your matrix A with a unitary matrix U. So U is an orthogonal matrix. Okay, orthogonal matrix meaning that U transpose U equal to identity. Okay? Right. So when you have a Frobenius norm of UA, right? So this is going to be equal to, well, take the square of it, just apply the trace formula. You're going to get A transpose U transpose UA, right? But U is orthogonal by definition, so this is simply trace of A transpose A, which is again the same as Frobenius norm of A whole square. Okay, basically pre-multiplying by a unitary matrix does not change the Frobenius norm, and that's very clear, right? Because when you're doing UA, what you're doing is you're applying this unitary transformation U to each and every row of A. correct? To each and every row of A, you apply this unitary transformation U. So basically, all the rows in UA will have the same norm as the corresponding rows in A. Okay, so when you take the sum of all the norms, you will simply get the same as the earlier. Right? So this is what you can also extend this a bit. You can actually say UAV, right? Frobenius norm of UAV whole square, where U and V are both orthogonal. V transpose U equal to identity, V transpose V equal to identity, right? So Frobenius norm of UAV whole square is again going to be the Frobenius norm of A square. Okay, so either pre-multiplying or post-multiplying. That's multiplying before or multiplying after with an orthogonal matrix will not change its Frobenius norm. Okay, this is also a very desirable property that the Frobenius norm has. It's called unitarily invariant. Okay, it's called unitarily because the extension of orthogonal matrices to complex valued matrices is called unitary, right? We are dealing with only real valued matrices in this course, but there is a natural extension that's possible when you allow your matrix to take complex entries. Okay. So unitarily invariant matrices essentially meaning that pre-multiplying or post-multiplying with an unitary matrix does not change the norm. Okay. Fine. You can also prove this in exactly the same way. You can take trace. So if you do trace, you will get trace of V transpose A transpose U transpose UAV. Right? So U transpose U is identity, so I might as well get rid of it. Just remove it from here. Then you will get V transpose A transpose AV. How do you know this is the same as trace of A transpose A? Well, you can just use the cyclic property of trace, right? So remember, trace has this very nice cyclic property, meaning that any matrix here you can actually move it to the front. The trace will not change, right? So you can write it as V transpose A transpose A. But V transpose is again identity, so this becomes trace of A transpose. Okay. Or you could simply apply this result to the transpose. Okay, and then you can conclude the same thing here. Okay. Fine. So that's the unitarily invariant property of the Frobenius norm. Okay. Fine. Now that we know a lot more about these eigenvalues and all that, we can actually also write the Frobenius norm in terms of the eigenvalues of a matrix, right? So let's say you have a so remember, Frobenius norm is not necessarily defined for a square matrix. It can be any matrix, right? Any rectangular matrix, you can define the Frobenius norm. Okay. So this is going to be equal to, so remember, it's a trace of A transpose A, right? It's a trace of A transpose A. But what is the trace of any matrix? The trace of any matrix is the sum of the eigenvalues of that matrix, right? So if you take the eigenvalues of A transpose A, I equal to 1 to n. Okay. You take the eigenvalues of A transpose A, sum of all the eigenvalues of A transpose A. Okay. This I would like you to recall that this is also the same as sum of the squares of the singular values of A. Okay, I equal to 1 to min of n comma n. Right. So if just a quick recollection, the singular values of a matrix are given when come from the SPD. Right. So you take U sigma V transpose. Every matrix A can be decomposed as U sigma V transpose. Right. The power of the SPD is that it can be done for any matrix, not just symmetric square matrix like spectral decomposition theorem, but for any arbitrary rectangular matrix, you can write U sigma V transpose, right? And the derivation was done basically by considering the gram matrices A transpose A and A transpose, right? If you recall from the second segment, right? This is the main idea, and basically the singular values of a matrix are the square roots of the eigenvalues of either A transpose A or A transpose. Okay. So if A is n cross n, it has min of n comma n singular values, right? So this basically you can also write the Frobenius norm in terms of singular values. Okay, very good. So in summary, what is the Frobenius norm? Frobenius norm is basically obtained by treating the matrix as just a bunch of numbers, taking the squares of all these numbers and taking the square root. Okay, you can also write it in terms of trace of A transpose A. You can also write it as trace of A transpose, right? It's the same thing. You can also write it as trace of A transpose, right? Effectively, what the Frobenius norm is doing is it takes each column of the matrix, takes their norm square and adds them all up for all the columns. Or similarly, takes the norm square of each row and adds them for all the rows. Okay, that's also another way you can think of the Frobenius norm. Okay, so this is the basic norm. What we'll do is, in the next part of this lecture, we'll look at other norms on the set of matrices.